So last week, we introduced conditional probability models, which was interesting because we moved to an action space that was entire probability distributions over outcome spaces. So our prediction functions now would take an input x from input space and then produce as an action a whole distribution on the outcome space. And then we would see what outcome actually arrived, and we were discussing that one way to evaluate how good a prediction was in terms of we're predicting a whole distribution now, say a probability density. We could evaluate the kind of quality of the prediction of the probability density in light of the outcome that actually occurred by seeing how likely this predicted density made the outcome that actually occurred. That was called likelihood scoring, like scoring the likelihood for a particular outcome for the predicted density or predicted mass function that you gave for that outcome. And given that approach to evaluating a single prediction, we kind of came up with maximum likelihood estimation, where given a kind of a whole hypothesis space of prediction functions, each one of which is a function mapping an input x to a probability distribution. And for a given kind of sample of data, a training set, we could see which of the prediction functions in the hypothesis space gets the highest likelihood on the data that we observed. So that was our maximum likelihood estimation approach to conditional probability modeling. All right. And we talked about some specific approaches like linear conditional probability models and these sorts of things. So that was a big break in the type of action space. Today, we're going to make another big break, kind of introduce another new set of concepts, which is the Bayesian approach to statistics and to machine learning. So in the Bayesian approach, the major change is that rather than choosing one function from the hypothesis space that we're going to settle on, maybe it's the maximum likelihood approach or however we choose to find that one function in the hypothesis space, in the Bayesian approach, we're going to end up with a distribution over hypotheses in the hypothesis space, which has some interesting consequences for expressing uncertainty and these sorts of things. All right, so that's all what we're going to get to. We're going to start with kind of almost a standard review of Bayesian statistics, which you might take in a statistics class. We're going to go not very deeply into Bayesian statistics, but give a flavor of it. And then we're going to kind of work from there and apply this Bayesian approach to the conditional probability models that we were speaking about last week. And one interesting thing, for instance, is that we're going to end up at another motivation for things like ridge regression and the kind of the L2 regularization. That's going to arise naturally in this Bayesian formulation. OK. So let's start with a quick kind of recap of what classical statistics is like, classical or frequentist statistics. So whether we're doing Bayesian or frequentist statistics, any kind of introduction to the subject will generally start with a parametric family of densities. So this is a set of probability densities indexed by some parameter theta. So for every theta parameter in a parameter space, we get a different distribution over our sample space, which here we're denoting by y. All right? So there's no input here. This is purely modeling distributions over some space. So we're keeping it simple for starters. OK. So just to kind of a caveat, throughout this lecture, I'm going to say density functions. Anywhere you see density functions, you can replace it with mass function. Everything goes through the same. The only difference is if we have integrals, we're going to need to replace those by summations, these sorts of things. If we were doing kind of a more mathematically advanced treatment of this, we could be in a measure theoretic setting, in which case everything's considered a density. A mass function is just a density with respect to another base measure. This is just a technical note. Anywhere you see density, you could think mass function, and that will get us pretty much everything we'll ever need in practice. So we have our parametric family of densities. And conceptually, we can assume that for one of those densities, for a particular theta, one of those densities governs the world that we're observing, at least the part of it that we are interested in. And if we knew what theta corresponded to the right distribution, then in some sense we'd be done. We'd know how to act in the world. We'd know what decisions to make. And in some sense, the whole point of statistics is what to do when you don't know theta, but you do have something else, which is a sample from that distribution, right? So we don't know theta, but we do have data drawn, IID, from the correct distribution, py given theta, the true kind of world-governing distribution. So statistics, a lot of statistics is basically, how do you handle the fact that you don't have theta, but instead you have this sample of data? And what can you, how well can you do with just the data? So one particular statistics problem is called point estimation. And point estimation is basically about trying to estimate with a single element of the parameter space what theta is. So, but let's use this to introduce a few more terms. So first, a statistic. Have we ever defined a statistic? A statistic is any function of the data. Simple as that. If D is our sample of data, then S of D could be any function of the data. And we're not restricting to real valued functions. These could be vector valued. They could be matrices. S of D could be a function itself. Like, for instance, a cumulative distribution function. That is a very standard statistic that people use in some settings. You could think of a histogram as being a statistic of your data, in that it's derived from your data. Okay. So it could be very generic, very abstract. Yeah, let me draw a quick picture, actually, to summarize what we have so far. So, because I want to set up this kind of correspondence between the parameter space, theta, here's theta, and the set of distributions, or densities. So let's, for simplicity, assume our outcome space y is one-dimensional, so we'll draw it like this. And so our parametric family of densities would consist of lots of densities on this set y. So I'll draw a few possibilities. There might be one, here's one, and here's one, right? So there's 3 densities, and each of these will have a corresponding parameter theta. So maybe this is theta 1 is that guy, theta 2, another point in the parameter space, corresponds to this guy. And then maybe the true theta is this point. Maybe that corresponds to this guy. Right? All right, so these are the possible densities governing our world. And then we have a sample, theta D. So how shall we write that? OK, let's just write that as kind of y1, y2, y3, and y4. So we have a sample that's 4 randomly drawn points from this density, because we assumed that was the kind of data generating density. And then what's a statistic? So a statistic is any function of these randomly sampled points. So one statistic might be, so let's call this data. One statistic might, let's call it S1, might be the sum of the y's, right? Another might be, you can imagine, a histogram of the y's. Why not? But there's one special class of statistics, and that's where the statistic returns an element of the parameter space, right? So we could also have a statistic, I don't know, S3 of D, which produces an element in here, And we could write that as theta hat. Hat, of course, because it's derived from data. Correct, theta hat of d. That would, of course, correspond to another density here, hopefully close to the right one. Right? Getting a little noisy there. All right. So we could write theta hat of d equals S3 of d. All right. OK. So statistic is any function of our data. Here's a couple examples. Here's 3 examples. One statistic was special because it's returning values in the parameter space. And such a thing is called a point estimator. So what would a good point estimator be? I mean, roughly speaking, if from the name, what we're hoping is that if we have a statistic taking values in theta, we might hope that it's coming up with, it has values that are close to the actual theta generating the data, right? That would probably be the point. So we'll say a good point estimator is when we have theta hat, in some sense, close to theta. All right. So how do we make it a little more precise? What are desirable properties of a point estimator? So there's a few standard ones. One is consistency. So here the idea is that your statistic typically adapts to the number of how big your data set is. And we could say that as the data set grows, the point estimator, as a function of n, converges to the true value of theta. That'd be consistency. Kind of asymptotically does the right thing. Another is the notion of efficiency, which kind of roughly speaking says that theta hat n is as accurate an estimate of theta as you can get for a sample of size n. Now, of course, this needs some setup to make more precise, but the point is that there's some efficiency is measuring some notion of optimality of the estimator. Other things that were kind of more popular in earlier years were things like unbiasedness. So maybe the expected value of theta hat is equal to theta. This doesn't seem as appealing these days. These sorts of things. OK. So these are all different things that you might hope that your estimator has. And the fun thing about Frequentist statistics is that you can make up any estimator you want. And once you make up your estimator, you have to convince somebody that it was a good idea to use that estimator. And so you would demonstrate or prove certain properties about the estimator. For instance, you might try to show consistency or efficiency or these sorts of things. So maximum likelihood estimators are very popular because they are, under reasonable conditions, consistent and efficient. So and they are kind of easy to think about, and often they're easy to compute, not always. OK. So that's our story about statistics and point estimators for Frequentist statistics. There's another notion I didn't introduce last time, although we were right there, but I want to call out some new terminology for you. It's the notion of the likelihood function. So we have this parametric model. And suppose we have a sample of data d of size n. And we can say, all right, well, what's the density for the full sample, d? Right? So we're assuming the sample comes IID. So we can break that up into a product of the densities of each of the things that we've observed. And that's the density for kind of the observation set that we have. Now, we can think of this as a function of d, the things that we're observing, and or of theta. But if we fix one of these at a time, so for fixed theta, we have a distribution, a density on data observations. On the other hand, for fixed data, we have this function of theta. So what does that mean? It's like, so suppose we've observed some data d, and now we still have this, so we lock down d, and now only theta can vary. So as we vary theta, we're getting a measure of the density evaluated at the data we observe for different thetas, and that's called the likelihood for theta given the data d. So to highlight the direct dependence on theta, we'll sometimes write it like this, where theta is in the argument, d, the data is fixed, so we put that in the subscript to kind of subordinate it. But it is just PD given theta. It's the density on the data observed given the parameter theta. This is called the likelihood function. So maximum likelihood is exactly finding the theta that maximizes this function for the data you observe. Okay. Any questions? Yeah.
In this notation of P, how do you indicate which one's fixed?
So PD given theta, in some sense, it's just a function of two things. So you have to indicate by context what's going on. So you might say, well, here's one way, for instance. If I write theta maps to PD given theta, this is emphasizing that this is a function of theta, d is fixed. Yeah, that would be a way to denote that. This would be another way. So by specifically putting only theta in the argument, that kind of says we're thinking about theta varying d fixed. Yeah. Good question.
The second bullet, you say that PD given theta is going to be the density function yn, but so currently it's only on subset d of y. So how can you have to extend it to yn? Or
I said.
Bottom bullet. Yeah.
Yes. So the extension. So d is a vector in yn. So d is. This is a collection of n samples from the sample space y. And this is where we describe how we are extending to the space yn. We are using the fact that the y's are independent, and so this probability on yn factorizes like this. Is that clear?
Yes.
Okay, great.
Yeah. So this means that the yi are independent, right?
Yes, I have assumed that the y's are IID, independent, identically distributed. That's exactly right. No, no problem.
I didn't know what IAD.
Oh, sorry. IID is some jargon from probability theory, independent and identically distributed. Thanks for asking. All right. Good to lock these basics down. Any questions on the statistics or the point estimations? All right. All right. So maximum likelihood estimators, as I said, would just be the maximizer of this likelihood function. A little bit more of a concise notation. And I just want to point out that, as I kind of have already, maximum likelihood is just one approach to getting an estimator, a point estimator for theta. We're not going to talk about other standard frequentist estimators, but just to give you a name, method of moments is another kind of popular one, a classic one in statistics. But today we're going to derive some point estimators, the map estimator and the posterior mean, which are really estimators coming from the Bayesian perspective, but you can consider them just as well in the frequentist setting. All right. So a quick example, which we'll return to again in the Bayesian, but let's start in the frequentist setting. Coin flipping. So we have a coin. Its probability of heads is unknown. Let's call it theta. So this is our parametric density model or probability mass function model. Parameter space for theta is some probability, so it's between 0 and 1. And so note that for any theta, each theta gives us a different probability model governing our coin. And we want to figure out which is the right probability model. What is the right theta? So let's gather some data. So we flip the coin. Each flip will be independent. And we get a sequence of heads and tails. And let's count them up. Right, n sub h for the number of heads, n sub t for the number of tails. So what do you think the maximum likelihood estimator will be for the probability of heads? That's the question we'll see. Yeah. NH over N, or NH plus NT. Let's try that real quick. So where shall we start? I want to do maximum likelihood estimator on this. What shall I write down?
Probably like the Bernoulli distribution.
The probability of.
Like it's a Bernoulli distribution, so we want to estimate.
There's some Bernoulli distribution going on here, yeah. So what's the definition of maximum likelihood estimation for a data set D? We've got to write down the likelihood function. All right. So we're looking for the maximizer of this likelihood function. All right. So what's the likelihood function for some data D? So let's do a warm-up. Suppose we have heads, tails. Suppose that's our data. Whoops. Data is equal to heads, tails. So what's the likelihood, or in this case it is an actual probability, because these are discrete. This is a probability mass function. So what is the probability of the data D for a parameter theta? Theta is, remember, probability of heads. Very easy, just say it.
HT over N. Number of heads.
So what is it?
2 by 3.
Theta times theta times.
There we go. So the probability of the data, HT, is, well, first we have to get a heads. So the probability of that is theta. And then we have to get heads again. So the probability of that is theta. And then we have to get a tails, which is 1 minus theta. All right. So that's the probability or likelihood for theta given the data D. All right, so let's write that as theta squared 1 minus theta to the 1. So how many heads were there? 2. How many tails were there? 1. All right. Is that clear? That quick example? All right, then. So likelihood, this is not right. It's not the likelihood of, this should be? Yeah. Likelihood is a function of the parameter theta. So the data goes in the basement. All right, and suppose we already made some nice notation for this. NH and NT are the number of heads, the number of tails. So there, what's the, let me just write one more thing. This is the probability of data given theta. And what is this equal to?
Theta to the NH.
Theta to the NH. So this is the probability for the NH heads, and then, right, it's 1 minus theta NT. OK, great. All right, so this is the likelihood function. It's a function of theta for the data D. Fantastic. And now we want to come up with a point estimator. We want to figure out what that theta is. Let's use the maximum likelihood approach. So we need to find the theta that maximizes this function. And this is actually a function. So if theta is one-dimensional, so here's a region 0, 1. If this is theta, we could take our observed NH and NT, and this is a function of theta, and we could plot it. And it will have a shape, and then we would maximize it. Yeah, I won't draw it because I don't know what NH and NT are. Okay, but let's do this symbolically. So we need to just differentiate. But as is often the case, there's something we can do to make this a little bit easier. Log, yeah. The log of this is a little bit nicer to differentiate than this directly. Here we have to do some product rule. Let's take a log first, because the argmax over theta of L d theta is equal to the argmax over theta of the log of the likelihood. Log doesn't change, which is the maximizer. So the log of this all right, and then we could differentiate this with respect to theta. All right, I don't think we have to work through the details. You guys know how to differentiate and maximize. Just wanted to kind of get you started. OK. So here's the, and as was perhaps obvious from the beginning, the maximum likelihood estimator is just the proportion of heads. All right, all set? Any questions? OK, great. Yeah?
The likelihood function.
Yeah.
It looks a lot like a binomial.
Yeah, sure does.
But it's missing the permutations.
Yeah, the kind of the choose part, yeah.
The choose part.
Right.
So we're not worried. I can think about this a little bit. But
No, let's discuss it. Go ahead.
So why don't we need that here? We're not worried about all the ways that we can get that in the heads.
Yeah, that's right. That's right. So the question is, often you'll see something like n choose n sub h out front. And I didn't write that here, and that wasn't accidental. So what we are doing is finding the probability of a particular sequence of heads and tails. So heads, heads, tails. This literally has probability, theta, theta, 1 minus theta. Now, if we wanted to know what's the probability of getting 2 heads and 1 tail in any order, that's when you have to do 3 choose 2.
But for a given data.
For a given, yeah. So for a given
Exact ordering, and so we don't have to worry about.
That's right. That's right. So I was kind of careful to write the data with parentheses instead of set notation, kind of to say, it's this particular sequence, this tuple of observations. Yeah, great question. All right. So this is our maximum likelihood approach. All right, let's go to Bayesian setting now for the first time. So the Bayesian setting introduces a new ingredient. It's called the prior distribution. It's a distribution on the parameter space theta, right? P of theta. So in some sense, we want this prior to represent, and this is an interpretation. Mathematically, it's a distribution on theta, end of story. There's nothing more to say. But if you want to kind of interpret it the way Bayesian statisticians do, we think of it as some distribution that reflects our belief about theta before we see any data. So for instance, in the coin flipping model, here's theta, ranges from 0 to 1. Now, suppose I give you an actual coin. You will, I suspect, be pretty confident that the probability of heads is close to a half. But maybe you've heard some things that it's not actually 50-50, but you don't remember which direction is more likely. So you say, OK, I'm not 100% sure that it's super close to 0.5. I'm going to put a distribution representing my belief that maybe, I don't know, maybe it's as much as 0.53 with some reasonable probability. And I might draw something like this, saying, I'm pretty sure it's a half, but there's some probability that it's not quite a half. And this is a probability density on 0, 1 on the parameter space that is my personal prior belief on what theta is without seeing any data. All right? This is kind of the full-on Bayesian interpretation and approach to prior distributions. So let's see what we can do with this type of thing. All right, so the Bayesian model, we still have the parametric family of densities that we had in the Frequentist approach, exactly the same. And now we have the additional piece, the prior distribution on the parameter space theta. Now, if you put these things together, you multiply together P of d given theta and P of theta, definition of conditional probability, basically, that gives us a joint distribution on the data and theta together. So I might come back to this, but the point we're making here is that in the Bayesian setting, there's really one distribution that governs everything. Because even though this was a collection of distributions indexed by theta, and that's all we have in the Frequentist setting, this prior distribution connects them all together by weighing them, giving explicit weightings to each theta. And we can combine that into a single distribution of the data and the parameter together. So the Bayesian walks around with one distribution governing one distribution, and the Frequentist has a collection of distributions. And so we'll see what the implications of that are. All right. So we start with the parametric family of densities in the prior, and the new outcome is what's called the posterior distribution. So posterior is our updated belief after we've seen some data. So we started here with our belief on what the theta probability is. Then we observed a bunch of data. D, heads, heads, tails, heads, heads, tails, heads. A lot of heads. Maybe heads is more likely, right? We could do some calculation, which we'll see in a second, and that will give us a new distribution on 0, 1 called the posterior distribution, the updated belief about theta after we've seen some data. And it might look like this. It's a little narrower. It's a little bit more certain. In this case, it probably is balancing a little to the right of 0.5 because we had more heads than tails. Okay. That would be called the posterior distribution. And what is it mathematically? It's the conditional distribution of theta conditioned on the observed data d. This is, from a mathematical perspective, this is child's play probability theory, P of theta given d. Okay, so how can we write this? Well, Bayes' rule, right? So what we know, because it was part of our Bayesian model formulation, is P of d given theta and P of theta. All right, so how do we write this in terms of those things? Bayes' rule. P of theta given d is P of d given theta.
P of theta.
P of theta.
By P of d.
Divided by P of d. And it seems like we've got to figure out a way to write P of d in these terms. Turns out we don't have to for our purposes. So I'm going to write this as follows. I'm going to write this as with the is proportional to sign. Is proportional to P of d given theta, P of theta. So this is seemingly an ambiguous notation. So one needs a little practice to interpret. So anytime you see a is proportional sign, let's take a simpler setting. So if we say, wow, if we say f of x is proportional to g of x, what does this mean?
Constant multiplied by g constant on x.
Yeah, great. So it means there exists some constant k such that f of x is equal to k g of x. And in particular, that you were highlighting, k, maybe there's hidden dependencies in these things, like with subscript d or whatever it is. K must be independent of x, the thing that we are considering each side as a function of. So if we come over here, for our typical case, we're doing things conditioned on some data d. So what's the variable in these expressions?
Theta.
Theta, exactly. So when we say is proportional to, what we mean is there's some k It may depend on d. It will depend on d, in fact. But it does not depend on theta. So theta is the variable of interest here. OK. So suppose someone just gives us this thing. And we want to get back the exact equality. You know, we need to actually do some calculations for whatever reason. How can we recover the proportionality constant in this setting?
Set theta to something which is more useful. Makes it simpler and set theta to something, say, 0.
OK. Oh, good idea. So you're saying, let's choose a specific theta, evaluate both sides, and then see what the proportionality, what the ratio is, and that's our proportionality constant. OK. That's actually a very reasonable approach. There's another approach that's a little bit more standard in these settings, which is to use the fact that this is a density, which means you know that it integrates to 1. Okay? So if we write this out as k p d given theta p theta, we don't know what k is, but we know whenever we find k, this whole thing must integrate to 1 because it's a density, because this over here is a density on theta. So we can write the integral of both sides is going to be 1 is equal to the integral of k p d theta p theta. K can come outside. We can solve for k. Here, let me do it in 2 steps. So k is equal to 1 over this integral. All right. So the point here is simply that we'll find that in most cases, the proportionality is sufficient. If we ever wanted to recover what that constant proportionality is, we have a method. We could just find the constant that makes this thing integrate to 1, because it's a density. OK. All right. So we ended up with this factorization, just from Bayes' rule, where we've lopped off p of d, because that was independent of theta. So we absorb that into the proportionality. And I just wrote this as kind of the mantra or the thing to remember in Bayesian statistics, that the posterior is proportional to the likelihood. This is the likelihood function. The likelihood times prior. Posterior is likelihood times prior. We're going to come across that a lot. All right. Great. So let's go back now to the coin flipping. So we're going to need a prior distribution on theta, the interval 0, 1. Now, last week we talked about some distributions, some parametric families of distributions with different properties. Was there a family of distributions whose support that lives on the interval 0, 1? Say again? OK, interesting question. So the suggestion was uniform distribution. There is a uniform distribution on 0, 1. That's a single distribution on 0, 1. I'm looking for a whole collection of distributions, a parametric family of distributions, all of which live on 0, 1. Someone had it last time.
Beta?
Beta distribution. Yeah, beta distribution. The beta family of distributions are all supported on 0, 1. Great. So the beta distribution will denote beta, alpha, beta. It has 2 parameters, alpha and beta. And the density is, we've already jumped to our proportionality notation. This has a nasty, not a nasty, but a somewhat complicated function as the normalizer, the beta function. And here's some example densities from this beta family. And you see a nice variety of shapes. Here's kind of a single modal distribution. Maybe if we had that but narrower, that would capture our prior that we were discussing earlier. We have these distributions that are favoring smaller numbers. these U-shaped bimodal distributions. So a whole variety of density shapes in the beta family. It's nice. And we need to come up with a prior. And that means that we have our choice. We could pick any distribution we want, any density we want. Something from the beta family usually suffices for this situation, but you're free to do however you like. There's certain advantages to beta computationally, but conceptually, you could pick any distribution you want as your prior. OK. So suppose we've chosen something from the beta family. So I've changed the parameterization from AB to HT, suggestively, for heads and tails. And just a few, just one property in particular of the beta distribution is that in terms of H and T, the mean of the distribution, right, these are distributions, it's H over H plus T. The mode, what's the mode of a distribution? If I were to draw a picture of a density like this, how would you know where to point to for the mode?
The most frequent.
So the mode in a list of numbers, for instance, or a list of data points is the one that occurs most frequently. But it generalizes. So the mode, you can have a mode of a density, or say again?
The highest value there, derivative is 0.
OK. So the peak, the highest value of this density occurs at the mode. So the mode of this distribution is wherever the peak occurs. So if this were differentiable, you could find it, for instance, by differentiating and setting it equal to 0.
We got it 10 minutes ago, right? With that same distribution.
We got what?
We do remember we differentiated.
OK. But wait, bless you. So this is the exact same form as the maximum likelihood estimator for theta when we had NH heads and NT tails. So the form is exactly the same. But this is, in some sense, totally different notion that we have this density, this continuous density, and we're finding the mean, the expected value of theta sampled from this density. Here, let me draw it differently. All right, suppose our density looks like. All right. So the mode be here. Would the mean be to the left of that or to the right of that? OK, good. Some cautious guesses that it's to the left. It is. The mean you could think of as like the balance point, and we have all this extra mass with a lot of leverage. It pulls things to the left. So if this were beta ht, this would be h over h plus t. And we, in fact, have a closed form for the mode for a beta distribution, as long as we're not in that weird shape that looks like this, which has no mode. So we constrain to ht greater than 1, which gives us that. And then the mode has that form. And so this is kind of generically how you would write the mode for a density, or a probability mass function. It's the argmax over the possible values of the density, or the probability function. Any questions? All right. Kind of mixing some terminology here from probability theory. OK. So the beta is a good one to get familiar with, as we're doing. So let's figure out what this posterior is. So what's the setup? So I shouldn't have written likelihood model. This is our probability model, our conditional probability model for the data. And so we want to figure out how do you update our belief on theta after we observe some data d. So we need to figure out this posterior density. you guys feel in the mood to work this out by hand, or you want to take my word for it? It's very easy. Preferences? All right, I'll slide through it instead of whiteboard through it to move us along. Yeah?
Before you start, our prior is beta HT.
Yeah, so.
But we haven't seen any data yet. So we're just saying that that beta is the family of distributions that is constrained by however many heads and tails I get in the.
All right, so.
How did you know to set alpha and beta that way? I guess. I mean, you can do whatever you want, I suppose.
Okay, so this is a bit. All right, this is a bit abstract. So before we were just writing beta HT as like a possible family of distributions. Now let's suppose we've chosen H and T as the parameters of our beta distribution for some H and T. So this we've made a decision. I just haven't told you what H and T are, but there's something. They're 2, 2, they're 10, 3. There's some H and T that I decided before looking at any data.
Okay, but you did definitely have to say what they were. Like, you locked down.
Oh yeah, absolutely. So I have to, and we'll do a concrete example later. So yeah, so step 1, something like H equals 10, T equals 12. All right. 2, collect data. 3, find posterior. So what that means, so we don't know a priori that the posterior distribution will be a beta distribution. So it might be some other distribution. So find posterior distribution on theta. It'll turn out that the posterior actually is the beta distribution. Very conveniently, it'll have a very nice form, which I guess we should just drive. OK, but yes, intuitively, beta HT, we've decided on a concrete HT. When we get data, D, it will denote NH and NT for the number of heads and tails. And this will be the probability for observing that data for any given theta. All right. So we want P of theta given D, the posterior of theta after observing some data. We know it's going to be proportional to, what will it be proportional to? P of D given theta, which we'll call the likelihood function, and P of theta, the prior. OK, let's write them down just to get going. P of D given theta, this is the thing we computed earlier, right? Theta to the NH, 1 minus theta to the NT. All right, that's P of D given theta. And then P of theta is also on the board. That's the density for the beta distribution for the chosen H and T. So that's theta to the H minus 1, 1 minus theta to the T minus 1. Now, how can we simplify this? You see how we can collect? Let's collect the thetas. Theta and H plus H minus 1. 1 minus theta and T plus T minus 1. Great. Now, this should look quite familiar, right? Theta to something, 1 minus theta to something. That is the form of the beta distribution. In fact, we know it must be the beta distribution because in some sense, there's only, so what's not exact here is this is a proportionality thing, right? But we know that it has to be a density. And if we have two density functions that are proportional to each other, they must actually be equal. Think about that for a second. If two density functions are proportional to each other, they must be equal. Because if they weren't equal, one would integrate to something different than the other. But they both have to integrate to 1. So this having the same form as a beta distribution must actually be a beta distribution. And so we can write this as beta. What are the parameters for this distribution we end up with? NH plus H and NT plus T. Any questions on this calculation? Very clear. All right. So let's summarize here. And this is very natural and intuitive. So one way to think about it is H and T in the prior distribution. Think of those almost as like initial counts for how many heads and tails we had. It's like we're summarizing our belief about theta in terms of fictitious data that we pretend we've already observed. Like our confidence in H and T is summarized as though we'd already seen 100 heads and 95 tails, something like this. This is a loose connection. So if that were the case, then our actual observations, NH and NT, get added into our kind of fictitious prior observations. That's kind of one way to interpret H and T. They're kind of an equivalent. It's equivalent to having an initial sample of some coin flips. All right. Any questions? So one thing that is not necessarily to be expected, but happens in this case, is that the prior distribution comes from the beta family, and so does the posterior distribution. It shows up in the same family. And this is a situation in which the term describing this is conjugacy. So the way you'd say it is that the beta family is a conjugate prior to the coin flipping likelihood, the coin flipping probability model, or the Bernoulli model, as you point out. OK, so we say a family of distributions pi is conjugate to a parametric model P. If for any prior in pi, the posterior is always also in pi. Right? So it's just a convenient. It's very convenient to choose a prior that's conjugate to your probability model so that this happens. This was much more important back when you needed to do things by hand. Now we have different sampling approaches where we can manage to, we can handle kind of non-conjugacy, ending up with some distribution that we don't even have a name for, but we could still handle it by, for instance, sampling from it, these sorts of things. All right. So let's make it concrete, this coin flipping example. So theta, let's actually pin down a prior. Let's say beta 2,2 is our prior, right? So that's what this prior looks like, a very cautious prior. I really think someone's trying to fool me with the weighting of this coin. It's very, very spread out, right? All right, now let's observe some data. We get 75 heads and 60 tails. So what is the posterior distribution? Let's just write it down. Posterior. Remember what the prior was? Prior was 2,2. Yeah, the posterior is beta 7762. We add in the prior counts to the posterior counts. The MLE, all right, the MLE. So this is let's estimate theta hat with some point estimators. We have the MLE that we described earlier. That's just a fraction of heads. So that's 75 over 75 plus 60. And the Bayesian thing that we get is this full posterior distribution. It's nice, more concentrated around a particular value. All right. So this is our belief after observing the data for what's going on with theta, the probability of heads. Is that clear? All right. So great. So the posterior is nice. It's nice to look at, right? It's interesting. What can we do with it? What if we actually need a point estimate for theta? What can we do? So what are your thoughts? What are different things we can do to pull out some single point estimate for theta from this density? Say again? Sure. You could find the theta that corresponds to the maximum, which is the mode of this density. Yeah. That in Bayesian terminology is called the map estimate, or maximum a posteriori. So the maximum of the posterior would be the map estimate, and that is indeed just the mode of the posterior distribution, posterior density. OK, great. Yeah?
Expected value.
Oh, fantastic. Expected value. This is a distribution. It has an expected value. That's another way to kind of come up with a single point estimator from this distribution. Great. Those are the two main ones. Any other ideas there? Yeah. Oh, just sidebar question.
If it's symmetric, then these both are equivalent, right? But on this picture, that's slightly different.
Yeah, this is not exactly symmetric. So that's right. And I mean, we had written down earlier on the board the exact difference between the mode and the mean. We had a formula for the mode, and you can see it's not exactly the mean, unless they're symmetric. Yeah.
We start with uniform distribution, which corresponds to an h and t equals to 1. We'll have pretty much the same picture, right? 76, 61.
Yeah, so if we had another prior distribution, beta 1, 1, which happens to be the uniform distribution on 0, 1, it'll be a very similar picture. That's right. That's right.
So basically, this means that after a series of experiments, we more or less get something.
Yeah, great point. Great point. So what you're pointing out is that we could see very clearly in this formulation that whatever prior we put will eventually be overshadowed, will be overpowered by actual data observation. And that's an important point. This comes to the fact that even if your prior distribution is in some sense wrong, and that it gives very low likelihood to the true value of the parameter, we will eventually, in any case, follow the data. Because NH and NT will grow very large and eventually overweigh H and T.
So, but in that case, we don't need a prior.
In that case, we don't need a prior.
Because
well, it depends why you think we need a prior. I'm just proposing the prior is another way to come up with, well, the Bayesian framework is just a whole nother thing. So, yeah.
So if we go to different set of functions, which are conjugate.
If we start with the conjugate prior.
Also with a series of experiments, you narrow down something. So you can have a set of functions, parallel functions, right? Which, okay, after this operation, one function transforms into another one of the same set. So they're conjugate.
Yes, so if you start with the prior in the family, the posterior will also be in the family. That's what.
But it will be narrower.
Right, so you're saying that it seems that the variance of the posterior will get narrower as we get more and more observations, which is certainly true in some sense eventually. But there are also situations where for smaller data set sizes, the variance will actually first grow and then shrink. Like for instance, if your initial guess, your initial prior, put all the weight in a bad place, and then you observe stuff, then the variance will get a little bigger before it gets smaller again. So there's an example of that, yeah.
So there's kind of two properties here. I'm curious if they generalize. One is that the order of our heads and tails doesn't matter here. And the other is that if we were to sort of do this in steps, iteratively, our step size doesn't matter. It doesn't matter if we take it in batches of 5 or batches of 1. We're always going to end up with the same beta function in the end, right?
Great. So the observations were two. One is that we only had to summarize our data in terms of the number of heads and the number of tails. The order didn't matter. And that is essentially, the order not mattering is derived from our assumption that the order doesn't matter, that we assumed that the data are IID. And the second question was, from this formula, you can see that as you collect more data, it doesn't kind of matter how you chunk the, first you got 10 and then you got 20. And that's also kind of a recurring consequence of our assumption of the draws being independent conditioned on the theta.
So that'll come out the same with different distributions.
Yes. It's a consequence of what's called conditional independence of the draws given the theta. The fact that the Bayesian would think of it as this notion of exchangeability, which is, for our purposes, we'll say conditional independence, condition on the unknown parameter theta.
So when you choose a prior, since the posterior is always going to be the conjugate family, is what you...
If we choose a distribution from a conjugate prior family, such as the beta family, so we have a distribution that lives in that beta family, then the posterior distribution will also be in the beta family because, we worked out that it is, and that scenario is called conjugacy.
Okay, so if you choose your prior unwisely.
If you choose your prior unwisely, meaning bad, like it's, in what sense unwisely, just to be clear?
If you choose something that the shape is not like
Okay.
Poisson distributor or something like.
Oh, okay, so we choose a distribution, a prior that's not in a conjugate prior family. Is that what it's?
Okay. So what I meant was like, so you're choosing a prior based on your beliefs about the model, the nature of the model.
Yeah, you should choose the prior. Ideally, you're choosing a prior that represents your belief about theta before you see any data. That's right.
And what I'm saying is, if you choose a prior that is very far from what's actually going on.
Okay, so if you choose, that's another notion of badness. So if you choose a prior that assigns very low probability to what's actually correct, or very low likelihood to what's actually correct, eventually you'll be okay. You'll get enough data. As long as it gives any probability or density to the truth, to the correct thing, with enough data, you'll eventually recover from your bad prior. But yes, it will take longer. If you have a distribution that whose support does not include the true thing, then you're out of luck. So if your prior gives zero likelihood or zero probability to the correct theta, you'll never, obviously, your posterior will never put any mass on that, on the correct theta.
Can we think of the prior as kind of regularization?
Can you think of the prior as regularization? Absolutely, absolutely. That is the connection that we'll be making. Yeah. And that explains what you had in mind when you were asking, when you said, if we have huge data set, we don't need to do this prior thing. And that's reasonable intuition. All right, yeah.
So are there like tables where we would say, this is my parametric model? What are the conjugate prior?
Absolutely. So you can look up for a given parametric model, what are the conjugate priors? That's right.
And that would be a strong reason to maybe prefer one of those.
That would be a lot of this comes down to the software you're using, or if you're trying to do calculations by hand for some purpose. So, but computational reasons may drive you towards using a conjugate prior family.
If I wanted to use this in like an online learning setting, that would be really inconvenient to only be able to do it once by some methods, and then end up with a whole other distribution that I have to like go back and.
Right. So you're saying it with a non-conjugate prior, ending up with some strange distribution.
Which becomes my prior for my next.
Which becomes your prior for the next thing. That's right.
Figure out what to do with that. Yeah, it sounds bad.
Right. You're not doing things in closed form in that scenario. You're doing some kind of sampling methods or something like that. Yeah. All right. Any more questions? And then I think we'll take a break. Yeah. Let's take a question.
So you choose a prior that isn't in your conjugate family, and then you run it through your data, and it becomes something else. Are there cases where, like pairs of starting prior and parametric model, where they'll cycle?
So by cycle, you mean, so you start with a family that is not conjugate. So you take a prior you take a prior that's not part of a conjugate, that you're not thinking is part of a conjugate family. And then you get a posterior that now you could.
That's different from prior.
Yeah, so let me say one thing just to, this might be a useful data point for us, which is that in some trivial sense, the set of all probability distributions is a conjugate prior to any probability model. Think about that for a second. So suppose you have this family of all probability distributions, right? You start with a distribution in that family, and your posterior will also be in that family. So in some trivial sense, every probability model has a conjugate prior family. The question is it a family that's nice and easy to work with? The set of all distributions is not. I just wanted to go back very briefly to what are we going to do with this posterior distribution? I said suppose we want to get a point estimator of theta. You guys suggested the map estimator, the mode of this distribution is one possibility. Great, in standard usage. Another suggestion was the expected value of this distribution. Great, also in standard usage. But we could think more broadly. How about another idea? There's one more standard way that we actually talk about a decent amount to summarize this distribution. All right, we'll think about it later. OK, so more generally, Bayesian point estimator, we want the two we've spoken about, posterior mean and map estimate. Great. So what else can we do with the posterior? I mean, they're nice to look at, right? You get a sense for the confidence and how there's some shape to it, perhaps. This doesn't have a very interesting shape, but in general, there may be, you could imagine getting a posterior that's bimodal or multimodal, for instance. And that's not something that would be summarized by a single point estimate. So there's more you can extract from the posterior. One thing, though, that's quite useful in practice would be in the analog of a confidence interval. In the Bayesian setting, it's called a credible set. And in the Bayesian setting, we have an actual probability distribution, posterior distribution on theta. And so what we could do is find a interval, if theta is kind of a subset of reals, an interval that has a probability of at least, say, 0.95 for containing theta. So if this is our posterior distribution, we want a credible set, a posterior credible set. So we observe some data, say the posterior distribution. We can ask for a posterior credible set for theta. And so we look for a region that has 95% of that probability mass. And that would be a 95% credible set for theta. The nice thing about the Bayesian setting is that you can actually make statements like the probability that theta is in this interval is 95% or more, according to my posterior distribution. That would be the full statement. Whereas, I don't want to rehearse it, but if you have taken Frequentist statistics, you'll remember that stating what a confidence interval is quite a convoluted thing. Yeah?
Are there any rules about how you center?
Right, because so the question is, are there rules for how to choose this credible set? Because there are many subsets of the parameter space that have 95% probability. Here's a contiguous one. You could split it into two separate intervals. No longer would be an interval, but you could. There's all different ways. So there's no rule. There's different definitions you could talk about. You could find the shortest credible set, or just different ways. But I don't have a list of standard ones off the top of my head. Yeah. All right. So the most kind of Bayesian thing you could do with your posterior distribution is, well, in a business setting, you usually don't stop at, you usually have to take some action, right? You're supposed to do some action. And just like we did in the first or second lecture where we talked about evaluating an action in terms of a loss function, that's something that we could bring back here. So in some sense, what we do with this posterior distribution, it kind of depends on what we're trying to produce, what our action is, and what a loss function on that action might be. And that brings us to Bayesian decision theory, which is kind of a tweak on the decision theory that we talked about at the beginning of the course. So the ingredients, this is setting up kind of statistical Bayesian decision theory here. So a parameter space, as we've had all day, a prior distribution on theta. But now we've introduced an action space, which suggests we're not going to be satisfied with just the posterior distribution. We want to actually do something. We want to take an action that's kind of derived or informed by the posterior distribution, informed by our data and prior. And to do that, we're going to introduce a loss function that takes an action and theta, a true parameter, and produces some score. So usually our loss function takes what? It usually takes an action and something from the output space. So that's when we're, in some sense, trying to approximate the output or something. Here, our goal is parameter estimation, or something having to do with, in this case, the goal is something like parameter estimation, point estimation. OK, so we'll take a parameter. So in this setup, what we can do very nicely is ask for the action that minimizes the expected loss. Expectation with respect to what? The expectation with respect to the posterior distribution of theta. Or we could write that really as the expectation of the loss conditioned on the data d. Because the posterior distribution is exactly everything that you can know and derive after seeing the data d. Right? So we'll define this posterior risk as the expected loss for an action A, conditioned on D. So what's random in this expression? We're taking expectation over something. What is it? Theta, exactly. So we have a condition on the data D. We have an updated belief on theta. If we left off D, we could still do this. Without D, we could find the action that minimizes the expected loss with respect to our prior distribution on theta, if we get rid of the d. If we didn't have any data, that would be the right thing to do in some sense. You act according to your prior belief as best you can. But we can update this by conditioning on the data. And this is equivalent to kind of taking the expectation of theta with respect to the posterior of theta. All right. It's just writing out the expectation in terms of an integral with respect to the posterior on theta. All right, is this clear? Any questions on this? So this is kind of a way to very formally choose an optimal action in the Bayesian context. You minimize your expected posterior risk. All right. So let's talk about some specific loss functions. Suppose we want a point estimate for theta. All right, well, theta, I didn't specify, but let's suppose theta is real numbers. So this is kind of like a regression setting where there's an unknown real number. We want to produce another real number to get close to it. And so we know our loss functions that are convenient for that. Square loss is a fine one. So we can ask what action, what theta hat, can we produce that minimizes the risk? In other words, the expected loss conditioned on the data we observed. So that would look like this. I'll let you stare at that for a moment. So we're looking for the action theta hat that minimizes the expected square error conditioned on the data. All right. So what do you think theta hat is that minimizes this expression? Yeah, exactly. So the theta hat minimizing this is the expected value of the posterior distribution of theta hat. And the derivation of that is very close to the derivation on our second homework, where we found the Bayes prediction function for square loss. It's the same idea, the same mathematical mechanics. So in some sense, you already know this. OK. Here's an approach to derive it. We'll leave that to the reader to go through. OK. So we end up with the conditional expectation of theta given the data D. So that's called the Bayes action, in that it's optimal with respect to our risk, our posterior risk. All right. So we don't have to do just square loss. We could do absolute loss. Why not? And so what's your guess for what theta hat will be minimizing the posterior risk here? Thanks. Yeah. So the median of the posterior distribution. So that would be yet another way to get a point estimate from a posterior distribution. You could take the median. And that would be optimal if we're scoring our performance, if our loss function is this absolute loss. All right. What do you think would happen if we use 0, 1 loss? So now let's go to a theta is discrete case. So theta, OK, here, English and French. Maybe we're trying to do language identification. So we're trying to estimate what language was this input. 0, 1 loss. So we have a distribution, a posterior distribution on theta. And we get a point if we got it right, and 0 if we don't. How do we? Well, we get a point. It's a loss. So we get a point if we get it wrong, and 0 otherwise. How do we minimize our loss here? Yeah, the mode of the distribution. Exactly. You want to predict the theta that's most likely under our posterior distribution. All right. OK, so we have the mean, the median, and the mode of our posterior distribution are all optimal actions to take under different loss functions. So this is kind of the most Bayesian approach to come up with the action you actually take. You come up with your posterior distribution, you come up with a loss function, and you figure out how to minimize your expected loss under the posterior. All right, let me just do a quick summary of what we have so far. So the prior represents our belief about theta before observing any data. The posterior is, in some sense, our updated belief, our rationally updated belief after observing the data D. So anything that we want to do afterwards, if we want to act kind of rationally, it should be based on the posterior distribution that we have about the world, about theta, in terms of, for instance, this Bayesian decision theory we had. So the key distinctions between the Bayesian approach and the Frequentist approach. Remember the Frequentist approach to estimating theta, for instance, we came up with maximum likelihood. And I said, well, there's these other things too, method of moments. There's different ways to come up with point estimators in the Frequentist setting. And your responsibility as a Frequentist is to justify your choice of the estimator you used with some properties. You prove it's consistent or efficient or unbiased, minimum variance, these different things. And you have a choice. You could go to a statistics book and find lots of different ways to come up with estimators. OK. None of that is the case in Bayesian. In Bayesian, there's no choice of a procedure to choose. Your choices are the prior, the probability model. I used to write likelihood model, but conditional probability model. And if you go as far as decision making, you need a loss function. After that, everything is computation. There's no other decision to make to, in some sense, act optimally. So a big part of the game in Bayesian statistics is how do you do computation to actually come up with the optimal action or the posterior distribution in cases where things don't work out as nicely and easily as they did for our beta binomial, our beta Bernoulli coin flipping case. So that's what a lot of research in Bayesian statistics is these days. A lot of approximation methods and simulation methods, Monte Carlo, these sorts of things. All right. All right, and then just the final recap. The Bayesian method Defining the model is as simple as, or is 2 steps. It's the family of densities, which we also have in the Frequentist setting. And we add in this extra piece called the prior distribution on theta. We compute, after observing some data, the posterior distribution. And finally, any actions we take should be based on that posterior distribution. You could do that by introducing a loss and minimizing the expected loss according to your posterior.